right, so now we're going to look at something called the first derivative test, and it's going to make it a little bit easier to find local maxes and mins. All right, so the test says this. All right, suppose we have a continuous function, and c is a critical point. All right, remember, critical points are when our function is zero, or sorry, our derivative is zero, or the derivative is undefined. All right, if f prime, the derivative, changes from positive to negative, then f of c is a local maximum. So let's see what happens. We have kind of c in the middle. All right, to the left of c, my derivative is positive, and we know positive derivatives are increasing. So to the left of c, my function is going upward. To the right of c, my derivative is negative, and that means it's decreasing. All right, like that. And what happens if it changes from positive to negative at c? That's going to give me a maximum right there in the middle. All right, so using the first derivative test, if I know what happens to the first derivative at my critical point, I know whether it's a maximum or a minimum. All right, same idea for this one. We have c, but now my derivative is going from negative to positive. So my derivative is negative. It's a decreasing function. It's going downward. If it's positive, it's going upward. And what happens when a negative switches to a positive? I'm going to get a local minimum there at c. And the last thing is, what happens if it doesn't change sign at c? So it's possible to have a critical point that's not a maximum or minimum. I could have two different possibilities. It could be negative on both of them, so it's negative before c, and it's negative after c. It'll just look something like that, and that's not a max or a min because it's still going downward. Or it could be positive before c and positive after c, and again, that's not a max or a min. All right, so we want to see a change in sign of the first derivative, and that gives us a local extrema, and that's the first derivative test. All right, so let's say we had this function. We want to find all relative maximums of f of x. We only care about the maximums. All right, so the way we're going to do it, kind of similar to an example we done before. All right, we're going to take the derivative first, because if we're doing the first derivative test, you need the first derivative. And that's going to be 3 times 1/3 is 1, x squared plus 2x minus 48. And then what we're going to do now is make a number line. So to make our number line, first we need to set this equal to 0. All right, this one we can factor. We're looking for two numbers that multiply to 48 and add the 2. It's going to be positive 8 and negative 6. So we get negative 8 and 6 as our zeros. All right, so once we know where it's 0, we can use that to our advantage. We can make a number line. Negative 8's there. 6 is there. And again, we do these number lines because that tells us where the zeros are, which means anything in between these values is either all positive or all negative, because you can only change from positive to negative by crossing 0. So we're going to do some test points. And if we plug these values in, if we plug in negative 10, we're going to get 100 minus 20 minus 48. All right, that's going to be some positive number. So everything here is positive for my derivative. If I plug in 0, I'm going to get negative 48, and that's negative, so everything else is negative. If I plug in positive 10, I'm going to get 100 plus 20 minus 48. That's also positive. All right, so this tells me where my graph is increasing or decreasing because I plugged all of this stuff into my derivative. So if my derivative is positive, that means my graph is going upward. My derivative is negative, that means my graph is going downward. And again, when it's positive, again, my graph is going upward. All right, so you can see just by looking at this picture, at negative 8, we're going to get a maximum. At positive 6, we're going to get a minimum. So my relative minimum, our relative maximum happens at x equals negative 8. And then you'd have to plug in negative 8 into your function to figure out what the y value was. All right, but using this first derivative test, we make our number line of all the times my graph is positive or negative. Again, if my function switching, my derivative is switching from positive to negative, that's going to give me a maximum. It asks me for a minimum. That's when the derivative goes from negative to positive. All right, here's another kind of weirdly worded question. Kind of these types of things show up on the AP exam. All right, for what value of k does f of x equals x cubed minus 6x squared plus 9x plus k have a local maximum of 10? All right, so we're looking for a local maximum at a specific value. right, so the first thing we can do is we're trying to find a local maximum. We know that happens when the derivative changes from positive to negative. So we're going to take the derivative, 3x squared minus 12x plus 9. And just like the last example, we're going to set it equal to 0. That way we can make our number line. I can divide everything by 3 just to make the number smaller. And then factor. All right, so now I can make my number line. Pick my test points. And if I plug in 0, I'm going to get positive 9. So everything in this region is positive. If I plug in 2, let's see, 12 minus 24 plus 9 is going to be negative. If I plug in 4, 48 minus 36 plus 9 is positive. All right, so everything in that region is positive. So again, plugging things in my derivative, so this tells me before 1, my graph is going up. After 1, my graph is going down. After 3, it's going back up. All right, I'm looking for an absolute maximum that has to happen here at 1. All right, so my local max is at x equals 1. So let's plug that into our function and see what we get. We plug this into our function, 1 cubed minus 6 times 1 squared plus 9 times 1 plus k. 1 minus 6 plus 9 plus k. Negative 5 plus 9 is positive 4. All right, so when I plug 1 in, I know this is a local max because of the first derivative test, but I want this local max to be 10. So now I just take this and set it equal to 10. And that tells me that k is 6. So if I make k 6, it's not going to change the fact of where the local maximums happen because that's all determined based on the derivative. But it does change the value of the y value. So if I want to make it exactly 10, I have to make k equal to 6. All right, so this is the first derivative test. All right, these number lines are going to get used a lot in this unit. Figure out where your function 0, put those places on your number line, and then do a test point in each region. All right, because if you know one value in the region, you know all the other values. All right, so this number line thing is pretty important. We'll get more practice as we go through more of the objectives in this unit.